linear kernel, polynomial kernel, then the different type of the kernels we can use for solving our problem. We plot the results to visualize the regression process and to find out the best fit line and the best approximation for the given data points. So this is in short is the algorithm. These are our input points. Here we are using training with leave one out cross validation using the Gaussian kernel. So these are the traces is B1, B2, Bn. These are the numbers and these are the function which we are using. And combining these in a form of the functions, we are using this as a output function, which this is the combined response and this is the output function. So we have the matrix as x equal to x1, x2, xn. This complete process is the based on these weight functions, and this we are taking as the predictors as a mu1, mu2, mu1. Based on this, we have defined the function and then we are finding the solution of the function. Now, what is wavelet analysis? In short, wavelet analysis is the function which has the two types of the wavelet, as a father wavelet and a mother wavelet. And the definition of these are that if you are taking any wavelet and take the integral from minus infinity to infinity, it always gives us a one value. Then it is considered as a father wavelet. If it is giving a zero value, then it is considered as a mother wavelet. So main purpose of this is that any function is given, we are easily able to convert into the dilate forms, which is the 2 to power forms depending on the function value. And as we are dividing this data into the two forms, it is very easy to find out or the denoise that data. So basically what we have we define a scaling function which is nothing but the 2 to power j of x minus k. Based on this, we defined a subspace which is a vector space of this and collect all the data. Then we are collecting the subspace which is defined as a nested sequence of the subspaces, which are the combination of these. Then we have a combination of these, which is V0 is a subset of V1, like this thing. We are getting the subset. So we are basically going to the final state that which kind of the signal we are taking, which is should be a noise free. And then in the containment property, we are finding the subspace Wj, which is the orthogonal complement of the existing vector spaces. Since subspaces are nested, so it follows the direct sum property, and using that we are calculating these direct sums. Then we are finding the scaling function again to find out the mother wavelet, which gives you the psi function. And since W0 is a subset of this, so our main purpose is to find out or generate this sequence. And when we are getting this generation, then we are finding the solution of the problem. Now, firstly we decomposed it into the smaller part, and once we decomposed into the smaller part, so basically to make our signal as a noise free, and then again reconstruct that to find out the original wave. So this is the some construction and the decomposition of the data set. So basically our job is to find out, in short, suppose this is the signal, we divide it into two parts, which is the D part and the Cn minus 1 part. This is the denoised part, so we are leaving it. Again we are dividing this Cn minus 1 into the two parts as a Dn minus 2 and the Cn minus 2. So basically we are taking a data, we are leaving the noise part, and then we are dividing into the final scale of this structure. Same way when we have to reconstruction algorithm, we have the Dn minus and Cn minus m, recombine these and we are getting this structure, recombine and we are getting again this structure. So it is both phase decomposition and then the reconstruction of the structure. Basically, this torus algorithm is given as a combination of the multi-resolution mallet algorithm. So in short, I am defining this. You have any combination of the Cj plus 1. It is defined by this one. Using the discrete wavelet coefficient, we define this one. And this is the basically a weight function, which is Cjk minus Cj. So those two consecutive terms, we take the difference and then accordingly we define the weights. So this is the combination. Suppose we have a set S, which is a with combine of the n data points. So when we are decomposing it, we are decomposed into the n by 2 forms. We have the high and the low factors. High factors we are neglecting, which is a noise factor. The composition with the frequency, again we are dividing into two parts. So the data n is divided into n by 2 form, then again n by form, and like this thing we are continuously going on. These are the wavelet coefficient, and this is the reconstruction of that. You have a n by 4 coefficient, combining these you have a n by 2, combining this you are getting the n data points. So this is a synthesis of any data into the decomposition, and then using a wavelet method, again reconstruction of these data. So this is in general is a wavelet LSSVR. Calculate the Fourier transform of the time series. Select a wavelet function and set a scale to analyze. Create the normalized wavelet function for each scale. Calculate the wavelet transform for that scale and shift. Determine the Fourier wavelength. This repeat the step till the we draw the get the wavelet spectrum. So in short, we have original signal with respect to time. Apply the discrete wavelet transform to find out the approximate coefficient as a CA and the detailed coefficient. From these two, we are extracting the vector or the feature of that vector. Then whatever information we got, we train and validate using the least square support vector regression. Using that, we predict the future, and then we calculate the performance measure, because to find out whether whatever we are doing, it is error free or it contains the error. So we define the, as we are getting the error to be a minimized, means basically whatever we are forecasting, if we are closer to the observed values, then we said that it is a good approximation. So this is the basically already I said that here we are using the wavelet as the Debussy 8 wavelet, using the input as a LSSVR method. So LSSVR type we are taking using, already I explained, 10-fold cross validation. Gaussian RPF we are taking to define the function. Now these are the different type of the performance errors. Main common is the mean square error, which is nothing but the defined as yi is the observed data and this is the experimentally or the calculated data. So if we are taking a difference of the square of these divided by the n value. So this is the actual value and this is the predicted or forecasted value. So if we are getting this difference square and divided by n, then if we are getting whatever with the value, that is considered as a mean squared error. Then we have a root mean square, which is a under root of the mean square error. We have the coefficient of determination. This is important. What we are taking from the given data, we found out the regression line. Find the sum of squared errors of regression, which is yi minus yi square. Then we have the sum of the squared errors of our baseline model. So this is the regression model for what we are forecasted, and this is the base model which is given. Now we calculate the ratio as a SSC by SST, and then R square is 1 minus this value. As we are coming closer to 1, means this error is negligible. So then we are getting a better to better approximation. This is the mean absolute error. Now we are taking a flow chart which we have used for wavelet least square support vector regression. We take the input data of the confirmed cases for like India and USA. We reprocess this data using the wavelet decomposition model. Here we have used the discrete wavelet transform, and then we divide this using this approximate coefficient and the detail coefficient. Divide this into the training and testing data. Once we are dividing into training and testing, we are applying the LSS via training process, and then we extract the information using the Gaussian kernel. We train the model and validate the result. Here we have used this leave on and out cross validation. Using this, we have used the LSS VR predictor, and then we simulate the processes by using these type of the errors which already mentioned, and then we try to find out that which error is the minimized error. Same way we have used the Mars method. Now this is the different type of the model which we have used here. Collect the data, then pre-process data, wavelet approximation, then select of the training and testing result, predict the future using neural falsification and forecasting the error. So for any three data, we use the neural falsification to find out the next fourth day data. So this is the process which we have used. Now what is the epidemiological modeling? Basically, any modeling is a simplified means of describing the transmission of the disease. So there are the different type of the model, and the most important thing is that how to formulate the equations and the parameters which we have to estimate. So why we need the epidemiological modeling? Basically, earlier we developed the modeling for the HIV, AIDS and the diseases, but recently for COVID, tubular, tuberculosis, and now for the diabetes even, and for the kidney problems, we are modeling the structures. So when we are modeling the different type of the structures, there are the basically types are stochastic processes or the deterministic